Hello guys, so I've been experimenting with a new oscillating setup to drive a Tesla coil. Um, Instead of going with the standard Armstrong oscillator, I have experimented and used some other oscillating designs. One of them was driving it with the kind of HF VTTC oscillator, which is a type of Hartley oscillator. That did work, but I had big problems with the feedback because the lamps were just getting too bright, because apparently that oscillator type is more suited to higher frequencies because you get more coupling between the primary coil and the feedback coil. So I've looked in this book here, and it also has a lot of oscillator designs. One of them is the push-pull oscillator that I tried once before, and which I will try again someday. Another good one has a bunch of good ones. Let me find the page. Okay, found it. Over here, it has a bunch of oscillator types. Over here, there's also a mistake. There needs to be a blocking capacitor, otherwise it will short out your coil. Forget these. These are just stupid things. I thought they don't work. Okay, so I actually decided upon this one. But it's not as simple as this. Yes, there is a choke, but there needs to be a DC blocking capacitor here. This capacitor can move over here from this side of the coil. Otherwise, you'll just short your anode through the coil, which at the first start I didn't really consider. I was wondering, why is it shorting out? Well, yeah. The book actually says about different decoupling techniques. Also, if you want to do some heating, you can do some. There's a lot of calculations here. There's another page. Let me find it. Over here. Yeah, so different methods where you can block DC over the coil. So yeah, you have an anode choke here and it goes here. The difference between this circuit is where the resonant capacitor is located. Over here you basically have it right parallel next to the coil, and over here it needs to resonate through your blocking capacitor too. On my setup, the capacitor is just straight across the coil, and this is the DC blocking capacitor. Over here is the anode choke, and this is configured as the Hartley oscillator. Let me show the schematic. Well, here's a schematic. So we have the standard microwave oven doubler. You of course have the filament supply and decoupling capacitors on the filament to shunt the RF across the tube filament, because otherwise your filament can heat up more than it's supposed to and it will break. And over here we have the anode choke, which is comprised of 4 chokes. We have the DC blocking capacitor here. We have of course the coil with the feedback. The grids are actually grounded. All the 3 grids are grounded, and the earth reference point is actually the cathode. Because the thing is, if you have the microwave oven transformer as your earth 0-volt house wiring reference, you could theoretically get an arc over between the filament transformer and the primary of it, because the cathode is actually the thing that kind of moves up and down the voltage on it. And this is how it can bias the grids positive, because if the cathode is driven more negative, because the voltage swing on this coil, it will go negative, and thereby the grid will be positive in reference to it. So yeah, you need to be careful of that. In the manual, it's actually also a reference. It also tells you where you can connect the earthing point, and for this oscillator design, they recommend it to put it on the cathode of the tube, which I understand. The secondary, that's the secondary. I don't have the dimensions because I still need to figure out the exact resonance frequency of it. It's behaving a bit weird, but through trial and error I found out it's somewhere between 2.2 and 2.7 megahertz. Right now this oscillator is untuned. It oscillates around 2.9 megahertz. So yeah, there's a lot of optimization to be done. I need to change the turns ratio, maybe use some thicker wire here too. And yeah, there's a lot of optimization still needed, but it does work. It's powered up. This is the warning light. Over here, the warning light, the mod is currently off. So yeah. Also, you need to be careful because you can get arc overs happening. Yeah, this wire was resting on this wire, and you can see what happened. This is where the B plus comes from, and this is the basically the cathode. So basically, it was right across 0 volts to the anode supply. And the problem is, it's not just the anode voltage. No, it's the high frequency high voltage that is also on this point here. So yeah, that's why it also arced through. I need to clean this wire and heat shrink it or something. Cover it with a lot of layers of tape. Yeah. This capacitor is for the picofarad, 4 kilovolt ampere reactive. Not the best. It's a Soviet capacitor actually. But the thing is, I wasn't able to find anything online about that capacitor. But the good thing is the rating was still readable. Let's see. Yeah, it's centered enough. All right. So yeah, the scope probe is being used as a loop antenna, as a just basically as an antenna here, and it will display on the screen what the waveform looks like. Yeah, I also was scoping grid voltages of other oscillator with the HF VTTC style oscillator, and the negative pulse is so big that it actually fries those scope probes. But yeah, it was also a stupid thing of me, because apparently while moving the probe I changed the switch position slightly, so I was barely making contact and it burned the switch up. So not good. So let's see. Oh, another careful thing is with the feedback ratio, because I noticed that the too high feedback ratio, like a 1/3 ratio that is typically used in VTTCs, the tube. The tube is placed between the choke coil and basically ground, right? Ground to this. So in operation, the tube kind of shorts out the power supply, specifically when you have big amount of feedback. So the tube actually saturates. I had this before. The feedback tab was 2 points higher, and it was drawing 0.7 amps from the microwave transformer. So yeah, so that got upset. I could actually smell some burning enamel because it got so hot. And the tube wasn't doing so well either. The filament was getting brighter because the 0.7 amps need to also go through the filament to reach the anode. So there was extra heating for the tube filament, which is not recommended. So yeah, typically you want the tube to run maybe just a bit over its rating on the current wires. With the voltage rating you can almost kind of completely ignore. The only two relevant things you really need to pay attention to is filament voltage and dissipation of the grids, plus minus 10% or so. So yeah, let me turn it on. So you can see, if I trigger it, there we go, we have a waveform showing up on the scope screen, and we have some current draw. And that tells us that the biasing side of the circuit is working correctly. Because if this tube wasn't receiving a positive bias, we would get no current at all. Because in triode mode, at 1 kilovolt anode voltage, it draws 10 milliamps, which is like nothing. So in triode mode, this tube needs quite a lot of positive voltage on the grid to switch enough, because the distance between the cathode and the anode is so large. So let's see. I increase it more, you can see the waveform is getting bigger as I ramp out the supply voltage. And you get breakout. Now it's on 230 volt mains. So we can see it draws 300 milliamps at 2 kilovolts anode voltage, average of course, because it is doubled voltage, right? So the average of that, the peak would be 4 kV, and the average is 2 kV of course. So you can see it's working very nicely. The tube isn't dissipating much. Most of it is actually going to the coil, and the coil does heat up during operation. But yeah, the anode is getting a bit warm, but the arc is quieter than my usual VTTCs. Yeah, the anode is heating up, but it's not that much where it's heating up to. Very nice, very nice. Yeah. So that's it. I will, I will change the. I will maybe use a thicker wire. I will use more turns. With this setup, basically the resonance capacitor is this capacitor plus the tube self-capacitance, because as you can see, there's a resonance path through this capacitor through the tube grid down to ground, and also this capacitor here. And I've noticed that the capacitance between grid 3 and the anode, which is the largest capacitance, is around 20 to 30 picofarads. With 30 picofarads, it's also the extra capacitance of, you know, the leads going out of the tube, etc., etc. Yeah, I've actually compiled a list of the capacitances. Let me find over here. I've actually compiled a list of capacitances of different tube types. So we have the GU81M, we have the GU81, and we have the RS384-2, which is this tube right there. So you might think, oh, these tubes look similar to the GU81. Yeah, because the GU81 is based on the GU80, and the GU80 is based on this tube developed in Nazi Germany. So yeah, we can see the interelectric capacitances on the RS384. It's definitely smaller than the Soviet copy, because I've noticed when looking inside that the RS384 uses thinner grid wire, which then means less surface area and thereby less capacitances. So if you ever needed every single interelectric capacitance on the GU81, here you go. So yeah, we'll do some more experimenting today with this circuit. Might even produce more breakout, maybe even slap a second mod on it, I don't know. But we will see. I might add some more capacitance to the coupling. We will all see. Maybe I'll upload a second video even. So, bye.